Good evening, everyone. So today I'm going to talk about the paper Detect-Localize-Repair, which is DLR, a unified framework for learning to debug with CodeT5, which was published in EMNLP 2023 in the finding tracks. So first of all, every automated program repair takes an input as an erroneous program, and then it trains the neural network, and then it outputs the fixed patch. So the majority of the debugging tools falls into two categories. That is, the first one is program analysis based, which is basically a compiler based, but it is not scalable to large and complicated programs. The second one is the neural based, which automatically learns the program, but it carefully designs the code representations. But it actually hinders the capabilities to more diverse domains. So in here, they propose that line-level bug detection is more reasonable if we can use the large-scale bug fixes datasets. So the contributions of this paper is as follows. So they propose a unified Detect-Localize-Repair framework, which is also termed as DLR, using the CodeT5 to seamlessly solve three program debugging tasks. The first one is function level bug detection. The second is line level bug localization, and then the program repair. So it basically introduced two newly collected large-scale line-level debugging datasets in Java and Python. The reason why they introduced new datasets will be discussed in the coming slides. And so they conducted extensive evaluations on each of the debugging tasks and their combined tasks, where the model outperformed existing baselines with the baselines were all the pre-trained models with a significant margin. So the basic idea of this paper is a function is given, which is the function level detection. It identifies whether a function is faulty or not. And then it goes to this encoder and encoder part, where if the function is erroneous, then it checks which line is error. So 0 means that there is no error, and 1 means there is an error. So if it finds 1, then it means that there is an error in the function and in the specific line. And then using the CodeT5 model, it creates a patch for the given faulty line. So this is the overview of the CodeT5 DLR model. So as I mentioned before, that this DLR has this three types of frameworks, which the first one is the function level bug detection, the second one is line level bug detection, and the third one is program repair. And since this three process is very highly related, correlated to each other, and can complement to each other, so they tried training these three simultaneously, which is termed as joint training. So moving to the first one, that is the function level bug detection. So the task is to detect whether a function is buggy or not. So if it's buggy, then it returns 1, and if it's not buggy, then it returns 1. So using the binary label. So the input is the input code patch X. Then it learns the binary probability of b theta. Y here means if it's a function level binary label. If it's 1, then it is if y is equals to 1, then there exists a bug in the function, in the given function. And if it's 0, then there is no bug in the given function. So it's just parameterized by CodeT5 theta. So this task is basically optimized with a standard cross entropy loss denoted as L detect in the training. The second one is the line level bug localization. The task is to locate the error from the exact line if the function is termed as buggy. So in the encoder part, it checks each and every line, and it gives it as a binary classification, binary label again. So if the binary label is 0, then there is no bug in the specific line, and if there is error, then it gives it as one label to the given line, and hence we can detect which line is erroneous. So this task is basically formulated to compute the T5 y x, where x is the given code and y is the given whole like labels for each of the lines. So y goes from 1 to the n number of lines, which y denotes the parameter of the encoder of code T5. The binary cross entropy loss is denoted as L localized. The last one is the program repair. So the task is to translate the buggy program to the fixed version of the program. So the probability is given as follows. So here F denotes the fixed version and X denotes the given input NS code or NS program. So it basically calculates the product of this. Fj is the fixed version and F1, which is the previous sequence before the jet token, and N is the number of tokens in the target sequence F. And this is a sequence to sequence task, and it is trained with a standard sequence generation loss denoted as the L repair. So since all of these methods are highly related and it is complementing each other, so they have tried how about combining their losses in an end-to-end manner, and hence they try to prove that their model is after adding this all the three losses and working it simultaneously, their model could perform well. So this paper is all about combining all the three detect, localize, and repair processes together and to generate the patches. So is there any questions? Can I move ahead? So they have collected two data sets. The first one is for single line fix, which is in Java, and the second one is for multi-line fix, which is in Python. So the reason why they have collected two new data sets are because the first one is that most of the previous existing data sets are focusing only at the file level, and hence they wanted the function level. That's why they have collected the new data sets. And the second reason is that the previous existing data set does not contain the before and the after changes, since their data sets looks like this, where the before fix, the line number is there, and the before fix, and then the after fix is there. So they have collected using the commit changes from the GitHub repositories. And the existing data sets consisted of only fixing the single line, and they needed the data sets for multi-line fix also. So they have selected this 13 bug patterns in the single line Java dataset. So out of which they have said that the change identifier appears to be the most common mistakes, and whereas the swap boolean literal appears to be the least mistakes that was being committed by the user. So these are the statistics of the data set, which is split into the training data set, valid data set, and the test data sets. And the two types, the single line and which is a Java, and multi-line is written in Python. So here the projects means the number of GitHub repositories, and the instances are the number of the projects. So as you can see, the multi-line fix are more than the multi-line fixes are more than the single line. Of the example of the data set. So here, as I mentioned before, it consists of the line before fix and the after fix, but it also can include some other meta and project name, so that it metadata such as the commit message or the commit ID, so that it is easy to trace back the original bug information. So moving moving towards the experimental parts, the first one is the function level bug detection. So they have used different types of models, out of which CodeBird, Graph CodeBird, PLBird are the pre-trained models, and TBCNN is a tree-based CNN, which is basically assigning a label to a given code, and spot bugs. It's a static analysis based for Java for bug detection, which is mostly in the Java code. So that's why there is no Python, no figures for the Python. And as you can see that the CodeT5 DLR, which was working all together, was able to perform better than any other, better than even the pre-trained models. And even CodeT5D was able to perform a little bit better than the existing pre-trained models. So towards the line level bug detection. So here also all the three pre-trained models, CodeBird, Graph CodeBird, and PLBird are there. And the first one, this baselines is DeepLine DP, which is based on the hierarchical attention network, which divides the source code into three layers, that is function, line, and token. And the line VUL is based on a vanilla transformer, which actually scores are calculated by averaging the token scores. So here also you can see that the CodeT5 DLR was able to outperform the existing baselines. And CodeT5 DLR knew there was nothing written about it there was nothing about what is CodeT5 DLR in the paper. So next is the for the program repair. So they have compared their model with the three existing pre-trained models, and here also we can see that it was able to outperform. So here is one of the example in which change color in function bug was able to correctly fix the buggy code into the fixed code, but whereas here it was not able to fix the code, although it was able to find the correct line of the errorness, but it was not able to fix the program. This is because detecting the exact numeric value is quite hard for this model, and hence it was not able to predict the correct patch. So this figure shows the analysis of the bug detection using the F1 score, which was broken down by 14 bug patterns, which I showed in the previous slides. So here also we can see that the CodeT5 DLR was able to localize more bug patterns than CodeBird or CodeT5 detection model only. So concluding this paper, so they proposed a novel Detect-Localize-Repair framework for jointly detecting bugs, localizing bugs, and suggesting program repairs, which was like detecting bugs was using the function level, and localizing bugs was using the line level, and the suggesting program repairs using the program repair. So the model is built on the CodeT5 foundation model, and it is fine-tuned jointly to achieve these three debugging related objectives. That was function level, line level, and the program repair. So the evaluation result shows that training these three objectives together yields better results than fine-tuning on each objective individually. But the limitations, there exist two limitations of this. So the first limitation is that it does not provide a consistent signals across the three modules, which means that if the function is not buggy, but it still continues looking for the patches, like using the line level, and then it tries to repair the program, although the program is not buggy. And the second limitation is that it used only used the within function information for the three tasks. But as you know that functions can get some other function calls from other functions level. So hence this is using just the function information, which was supposed to be used as the additional information rather than the main information. The paper is all about this much. Any questions?
I have I have question about the line level bug localization. So line level localization is detect buggy line, right?
Yes. It's like first the function is detected whether the given function is buggy or not. Then it checks line by line whether it's whether each line is like buggy or not. So it's checking each line, and it is labeling with a binary ones. If it's buggy, then it's 1, and if it's not buggy, then it's 0.
So I have two questions about this strategy, and the first one is about the input, because if they use input as same as the other models like other tasks, they just ignore the line, right?
Sorry.
When we use when we use models, we use tokenizer and use for input.
Mm-hmm.
Then in this task, we use like that, and we just ignore all line separation. So I think that must be decrease the performance. So do they did some specific things for this test or input?
No, I don't think they have done anything specifically.
They just use input for input same time.
Yes.
And my second question is, all programs have different line length. So how they fix the shape of this output? Do they just limitation, or
How do they fix the shape of the output, which means that how do they, like, it's detecting only one line, right?
no. So in this picture, the localized output is different from every program. Like
Yes.
if a program have 4 ranks, and but encoder outputs have 4 size vector, and if there is 8 lines, the output is must be 8. But realities have a fixed size of shape.
No, actually it's not fixed. It depends upon the function which is getting inside, so it changes.
So my question is how they change to depend from the line length.
혹시 질문이 어떤 의미일까요? 저도 좀 잘 이해가 안 돼가지고.
저도 영어로 말하니까 잘 정리가 안 되는데, 그 로컬라이즈라는 게 라인 버그가 있는 라인을 찾아내는 건데, 그 프로그램마다 입력 그 라인 길이가 다른데, 이제 어떻게 여기서 저자들은 그러니까 4개짜리면은 4개가 나올 거고, 5개짜리면은 5개짜리, 6개짜리면 6개짜리 벡터가 나와서 그거를 크로스 엔트로피로 계산할 텐데, 그 프로그램마다 길이가 다 다른데 어떻게 고정을 시켰는지가 잘 이해가 안 돼서, 제한을 두고 리미테이션을 스레시홀드로 한 건지, 아니면은 뭐 여러 개를 돌려서 디코더처럼 한 건지, 이게 잘 이해가 안 됩니다.
So Mingi's question is, if you take the codes with different line numbers, right? Different number of lines, then the output of the model should be the vectors with a different size, right? So if the input code has 10 lines, then the output vector should be the one-hot vector of size 10. And if the code contains more than 10 lines, then the vector should be kind of larger than the previous one, right? how do the model produce this kind of variable length output? I mean, that was, I think, Mingi's first question.
So like they basically gathered the last layer states of all this SEP, like the separate tokens from the encoder, and they mapped them to a vector of the probability from like for each line length.
Oh, so you mean the T5 includes each line separately, not, I mean, take the entire code, right?
Yes, sir. Like they are gathering the last layer states of all the like SEP tokens from the encoder.
But
The separate encoder.
I mean, CodeT5 is trying to take the whole code as input, right? Not
yes, sir. So they are like it's taking it with the function, like function-wise.
Function-wise, but with different number of lines, right? Depending on the case, right? So how does this model can process?
Like it's counting the number of lines, and then it's mapping them to a vector of the length of the number of the lines.
Number of the lines.
Uh-huh.
So where did it? I mean, where was it mentioned in the paper?
So in the line level bug localization area, it says that specifically we gathered the last layer states of all SEP tokens from the encoder and mapped them to a vector of probability.
아, 민기 학생 혹시 지금 이해했나요? 아디티 답변을?
저도 이해 잘 못했습니다.
Can you go back to the figure 1 in your slide, Aditi?
Yes, sir.
여기 보면은 라인 끝에서 세퍼레이션 토큰들이 있는데 저게 라인 넘버 개수만큼 그러니까 있는 거니까 CodeT5 인코더가 이걸 처리하고 나면 저 세퍼레이션 토큰들마다 벡터가 생길 텐데 걔네를 어그리게이트 해가지고 쟤를 이제 저 세퍼레이션 토큰의 개수만큼의 이제 벡터로 매핑을 한다는 얘기 같거든요.
네, 이해했습니다.
네.
그게 맞는 것 같습니다. 그럼 첫 번째 질문도 다 이해가 되는 것 같아요.
네, 이거 신기하네. 이렇게 하는 건 저도 처음 보네요. 네.
따로 저거를 붙일 필요 없이 어차피 저 토크나이저에서는 다 뉴라인 토큰을 저걸 하면 되니까 따로 전처리가 필요하지는 않을 것 같습니다.
네, 아까 그 게레가 혹시 손들지 않았나요? 저 게레 학생?
Can you hear me?
목소리가 좀 작은데요. 좀만 키워주겠어요?
Can you hear me, Aditi?
예, 들립니다. 네.
Okay, thank you for your presentation. Can you show me on the joint training loss? Okay, I think here the bug detection and localization problems are classification problems. The third one, L repair, is machine translation problem. As my understanding, the classification loss functions are supposed to use cross entropy, binary cross entropy function. The machine translation problem, L repair, might be
the standard sequence generation loss.
Yes.
It uses the standard sequence generation loss.
Standard frequency.
Sequence generate, because it's a sequence to sequence problem, so it is trained with a standard sequence generation loss.
Okay.
And then it uses the beam search to generate the rank list of the fixed candidate patches.
Okay. It doesn't use negative likelihood function, the machine translation less?
No, I don't think so.
My question is, these are different objectives, machine translation and classification problem. Is it feasible to combine them to accommodate the joint loss?
I guess it is feasible because the results do show that it's being able to perform better than other ones, because these three processes are like highly correlated and they do complement each other, because in order to once after we detect it, we need to localize where it is actually buggy, and then we actually need to repair or create up the patches. So these three steps are like correlated with each other.
Okay, thanks.
아디티 방금 그 계례 질문은 L 리페어가 그 논문에 스탠다드 시퀀스 제너레이션 로스라고 되어 있는데 이게 네거티브 로그 라이클리후드가 맞냐는 거거든요. 근데 맞아요. 그 시퀀스 제너레이션은 네거티브 로그 라이클리후드 로스를 학습시키는 게 맞기 때문에 그거는 정정을 해야 될 것 같습니다. 예, 아디티가 아직 학부생이기 때문에 예, 여러분 좀 양해를 구합니다. 예. 예, 또 혹시 질문 있으신가요?
There is one question in the chat, the chatting box. It says that why the authors have used just the CodeT5 as the foundation model. Because the reason may be because they are using both the encoder and the decoder, and the CodeT5 enables the code generation, and it uses both the encoder and decoder, and whereas the code part does not uses the decoder part. And it says, are there any other key contributions rather than this? It's just using the three processes simultaneously, and that's all up with the contributions.
I have a very simple question. So is this technique applicable only to the line level detection, or is this technique also applicable to more fine-grained level bug detection, like statement or the expression level?
This is, as per the paper, this is only for the line level detection.
So can we easily extend this technique for applying more fine-grained level bug detection, or is there any technical challenge for extending this technique for applying more fine-grained level?
Right now, sir, I am not very sure about it. Maybe we can go for the statement level also, but I'm not so sure with my words right now.
This is because
I'm sorry, sir.
This is because I think the performance of program repair for fixing more realistic bug would be unsatisfactory without considering the statement level bug detection, I think. Okay, thank you for answering the questions.
Sorry.
네, 혹시 또 질문 있으신가요? 네. 만약에 없으시면은 예, 여기서 마무리될 것 같습니다. 저희가 그 백그라운드 설명 부족했는데 아무래도 저희 연구실 그 아디티 학생이 지금 학부 연구생으로 그 공부한 지가 아직 1년이 좀 안 돼서 네, 아무래도 좀 여러모로 조금 부족할 수도 있었는데 예, 인내심을 갖고 들어줘서 감사하고요. 이 논문은 EMNLP 작년 그 파인딩 트랙에 그 실린 논문인데요. 저 NLP를 하는 사람들이 사실은 그 SE 쪽에 대해서 이제 많은 지식을 갖지 못하고 있기 때문에 아무래도 차 교수님 말씀하시는 것처럼 좀 더 이제 구체적인 뭔가 뭐 버그 리페어라던가 뭐 이런 것 리즈닝이라던가 뭐 이런 것들은 전혀 안 되고 있다고 보이고요. 근데 그럼에도 이렇게 랭귀지 모델을 사용해서 오토메이티드 프로그램 리페어라던가 뭐 근데 차 교수님 말씀해 주셨지만 이전에 버그 로컬리제이션 이거 자체로도 사실 굉장히 어려운 문제고 근데 이런 것들을 이제 동시에 함으로써 뭔가 시너지를 발생시킨다 이런 것들이 저는 개인적으로 좀 재밌게 느껴져가지고 또 가능성이 있다고 느껴져가지고 예, 이걸 저희가 내부 세미나를 한번 했었습니다. 그래서 뭔가 지금 하고 계신 연구 관련해서 이런 테크닉을 뭔가 적용할 수 있는 게 있으면 조언 주시면은 예, 감사하겠습니다.